what we see our laser spot essentially. So we can actually see it transversing on the screen, as well as, instead of trying to actually look inside the optics block, which is pretty difficult. So it's nice because we can actually see if it's close to the edge, things like that, things that might affect our data. And it also, there's other graphs and stuff that we use that provide sort of like a nice user interface in order to look at what our data is coming out as. So what we're expecting to do is provide data that's about 100 times more sensitive than the current Washington's current data. So this is the sort of predicted line that we're going to exclude from the Yukawa potential. And our goal, hopefully, is to get about 100 times sensitive. The problem with that is that that sensitivity is really difficult due to a lot of noise. So most of what we do is try to exclude noise, and that can be very difficult. So things like shielding wires and pretty much everything you can think of to reduce noise. So we're studying gravity because there's a lot of theories out there right now that we can actually probe at this level. Obviously, gravity is very weak, so it's been very hard to do any sort of tests on small distances. Things in cosmology are, I wouldn't call it easier, but possibly more accessible due to the fact that you have very large bodies. So we can, we studied large bodies, gravitational stuff from there, and so we're trying to provide world-leading tests for small-scale gravity. So it's exciting. We have a lot of prospects for what we're doing, and it will affect a lot of areas of physics. So there's a lot of theories that are, like I said, string theory and dark energy, that are kind of relying on tests that have predictions at this level. So hopefully we can either help them out or exclude that, so those theories don't actually get to make those predictions anymore. So that's currently what we're doing, and Holly will provide more on some of the stuff I didn't talk about.
Got about 10 minutes for questions.
Sweet.
So what the main source of inaccuracies in the experiment, like the noise or problem of determining the small angles, or what the main
the main problems that you're seeing? Noise is actually a huge issue. We have, basically our signal is so sensitive that anything, including the Casimir effect, which is tiny, and that's something that we're gonna have to stretch a membrane across between our apparatus, between the pendulum and the test mass. So there's quite a lot of hurdles to overcome when it comes to reducing noise, and to get that sensitivity, the nanoradian sensitivity that we need, there's a lot of procedural sort of reduction of noise. Things like using BNC cables in order to have everything shielded. Shielding our apparatus in many different ways is also what we're doing slowly to kind of get there, but it's been pretty difficult and just a lot of time-consuming steps in order to get there. So I don't know if I answered your question. What was the beginning?
How much have you reduced it? By what factor already have you?
I think we've reduced it by about 100 magnitudes. Do you know, CD?
Yeah, we're within a factor. It's about a factor of 10 of what we need to be, or so.
Right. So we're getting there, but of course it gets exponentially harder as we get down to the fundamental limit of noise. So.
This might be a ridiculous question, but why would you expect inverse square to be violated by an alpha?
You mean for the Yukawa potential?
Yeah.
I'm not really sure why that's sort of the derived expectation, but it has. I think it's because it's sort of a general. It has. Do you know, CD? Could you explain that better?
I can elaborate if you like. The exponential is kind of the industry standard way to characterize a deviation from the inverse square law, because it has all power laws contained in it in some sense, right? So you could look for power law deviations, or anything that's going to deviate from 1 over r squared will show up with some at least non-zero value of alpha and lambda.
But since there hasn't been a deviation, it's sort of just the general equation at the moment.
Simplest way in some sense.
So, its original purpose was to describe force particles that have mass, right? Mesons, and so I wonder if that you're looking for some deviation away from a zero mass. I think if you had just another zero mass particle, you'd have still 1 over r squared. Right?
Well, but these extra dimensions show up as some non-zero value of alpha. How you interpret alpha and lambda depends on whether you're talking about particles or extra dimensions or dark energy.
So in extra dimensions, it might naturally rise.
Right, and so it's a more general way of looking. To interpret it in a specific scenario would require a little more theory, but. We're kind of looking for a general deviation from the inverse square. Sure.
And also, is it sensitive enough that we would consider the momentum of the reflected light? That can affect the, tilt the sensor. This mirror by this nanoradiance. Is that sensitive, or it's doesn't have any problems? So with the light pressure on the mirror.
Right. I don't. That's a good question. I think that the size of it. We have a pretty small pendulum, but I think the size is large enough that I don't think that that any sort of pressure from our laser would affect it. But I also think that since we're pulsing our laser, that there might be something that we could subtract out if it does show up. I think that it might be visible.
We're also looking for an AC twist of the pendulum, and that's a DC pressure coming from the light. So
that being the fact that it is pulsed, it might
the first order
might show as AC. Yeah. So, and that's one thing that there's a lot of effects that could show up as DC, and that we're looking for any sort of actual AC twist. So that could being the fact that we're modulating our attractor mass, it might actually we're hopefully looking for only AC kind of deviation. So we'll see.
How is the apparatus vibrationally shielded from the building? 'Cause I'm sure, in a building, elevator.
That's a good question. And Holly will answer that. She has, in her next talk, she'll go into detail on that. So,
just as a number, the frequencies we're looking at are oscillations that happen at 100 seconds or so. So really slow type stuff. So we don't care so much about high frequency.
That's sort of related to what I was going to ask. Why did you choose 10 hertz?
we actually had a different signal at first, but we had some problems with reading the data at that rate. So to reduce noise, it seemed to look a lot nicer at 10 hertz. So it's really just a way to use our lock-in amplifier to kind of lock out noise. But it's not I don't think it's set in stone, but that's what we've been using. So.
Are there gravity wave people interested in?
I'm not sure as much on the gravitational
answer
wave
at all. I mean, does it give rise to gravitational wave damping if there's another term or something like that?
I think that on these small scales, it's not really something that that would concern like gravitational waves.
It's more the high energy physics community is really interested in this kind of stuff, and cosmologists, but the gravity wave people, not so much.
Other questions? Well, I think we can. It's not a tragedy if we get 5 minutes ahead of ourselves. The next talk, since they're related.